as I said in the previous lecture, we convert the message letters. What are message letters? Message letters are just some alphabets. For example, A, B, C, D. For example, in DNA, you use T, C, G in those alphabets. So in any language, in English, we say A, B, C, D, E, and the alphabet. So you send the alphabet. In machine learning, we encode our data space, you quantize it, and then you have some alphabet. So you can always quantize your data into some alphabets. Let's call it A, B, C, and D. But as I said, to reduce the redundancy, we should use the bandwidth spectrum efficiently in order to send your signal. And that's why, for example, to send A is an alphabet, we use probability of 1/2. To send message B or message C or D, for example, message D is 1.8. And so the algorithm is like this. You put this into one cluster and you put the rest of them in another cluster, because 1/4 plus 1/8, 1/8 is 1/2. By the way, we call this cumulative probability. So we represent this by 1, we represent this by 0. So we have 1, 1, 1. If you carry like this, so we got the most significant bit. So in the next layer, we get the same thing, we get the same idea, and what we get is 0, and then we cluster them together, so you get 1 and 1, and you got the idea. You cluster them together, so you can code that. So what is the average? The average is the probability times that Li. So P1L1 plus P2L2, it becomes 7/4 with these numbers. And L mean is just h of xi, which is just the entropy, which is Pi II, which is log of 1 over Pi. And finally, the efficiency is L of mean divided by L of average. So let's say the Shannon-Fanon coding for this example that I gave you for A, B, C, D symbols is like this. First, you get one cluster, and B and C and D are in the next cluster, B, C, and D. And then you get B, but C and D are in another cluster. And finally, C is separated from D. So this is the idea of coding. So we have coded. So what we have done is we have coded some symbols like A, B, C, and D. And of course, we have a method of them. Maybe D, B, B, A, C. It's a message that we're sending to the other planets. So the message is like this, and we code that. For example, it is 10011. So we code that. So for any message, we have a code. So from now on, when I say the message, for any message, we have a code. So there are lots of ways to do this. And for example, let's talk about discrete memoryless channel, that's YK. So a memoryless channel, you have a channel, you have XK, you have YK, the output. So we have a channel matrix, and YK depends on XK only, and not on the past, only on the it just depends on XK. So the channel matrix is YK divided by XK, which is equal to, for example, we write it like this: Y2 X1, YN X1, YN XM. So you got the idea. And we can also have a lossless channel. So this is a memoryless channel, but we may have a lossless channel. So in a lossless channel, X1, X2, X3, Y1, Y2, Y3, Y4, Y5. This is 1/3, this is 2/3. So you should always know that the sum of the rows is 1. So this plus this is 1. And the next one is, for example, 2/5, 3/5, and 0. So the sum of this and this is 1. And finally, we have 1, only 1. And another example which is very important is binary symmetric channel. For example, you have X1 with probability P, you get Y1. X2 with probability 1 minus P, you get Y1, but with probability P, you get Y2. And finally, you get 1 minus P with probability, we get Y2 with probability 1 minus P. And so the matrix is like this: 1 minus P and P. And for example, if you have a probability, input probability, for example, 0.5, your output is just multiply this 0.5 by this matrix, and you get 0.5, 0.5. So for this special input, you get the same thing. And what is channel capacity? Channel capacity. You know, when I talk about this, I imagine the equivalent of that in deep learning, in neural networks. So for each of these concepts, and for each of these sentences that I say, there is an equivalent sentence in the context of deep learning. So always try to find analogies within analogies, up to infinity. So the channel capacity is the maximum rate of information from transmitter to receiver, and we denote it by C. So this is the maximum rate of information. So if your information rate R is less than C, which is the capacity, then transmission without error, even in the presence of noise. Transmission without error. Because the capacity is large enough that can handle that. You can use anything or error correcting codes or anything. But if your R, your information rate, is even larger than your capacity, then it's very bad, because error-free transmission not possible. And finally, I summarize everything by saying this theorem that says the channel capacity is equal to bandwidth B log 2 of 1 plus signal over noise. And we count it by bits per second. For example, 8 megabits per second. And so this is the bandwidth. It is very expensive. Bandwidth is expensive. Signals to noise, everything is about whatever it is in your medium. If it is mountains, if it is very noisy factory, so noise depends on the environment that you live, and so signal to noise is, if it is high, then your capacity is higher. But bandwidth is like the money you have. It's expensive. So if bandwidth is higher, your capacity, channel capacity is higher. And let's talk about error control coding. So you have a message signal. It is k-bit. You give it to channel encoder. And then you multiply it. You know the modulator, because I studied electrical engineering. We know all of these modulations, AM modulation, FM modulation, and digital communication is all about these kinds of modulations. So you multiply it by some carrier or those things, but now in n bits. And then the modulated signal goes to the channel. So you add noise to that, because the channel, as I said, is noisy. And then you get the demodulator. Demodulator, because the carrier is removed from the signal. And then after that, you go to channel decoder. So everything is reversed now. Just like the autoencoder in deep learning, you have encoder and then you have decoder. So you can think about like that. And then you have received signal. You know, in variational autoencoder or any generative model in deep learning, you want, if you have X here, your original image or original text or original communication signal, you want to have the reconstruction error to be as, what is reconstruction error? It's X minus X hat. Okay, this one may be much better. Or if it is a message, you need Hamming distance. So Hamming distance between X and X hat. So you want the reconstruction error to be as small as possible. Just like a variational autoencoder, you want the X minus X hat to be as small as possible. So your channel encoder is for example, this is the encoder of a variational encoder. Channel decoder is the opposite, goes from latent space to the signal X, now X hat, because it's just the approximation of X. And so you see that there is an equivalent between whatever we do in electrical engineering with whatever we do in deep learning. And because information theory is the basis of analysis of the things, and compression is also related to generalization in machine learning. And I don't know why people don't talk about it, because it's very important. Only a few people like that Jewish computer scientist in Hebrew University knows about the importance of these ideas of information theory and using information theory for generalization and deep learning. And that guy who introduced information bottleneck is very amazing scholar. He's a very genius guy because he was so brave to relate deep learning to classical information theory that people think that it is only related to communication and 5G technology in those things, but you can use it in machine learning as well. So the types of error detection in correction coding are, for example, you have retransmission request, but it is bad because it produces delay. So either you need to retransmit everything, but it produces delay, or you can use forward action error correction. There are lots of coding, so most of them are block codes. And block codes, Hamming code is very popular. Hamming code and BCH code, cyclic code, RS code. And the other type is convolutional code. So either turbo code or trellis code. So they have memory elements. For example, in block coding, you have a message. So your message is converted to k bits and some parity, n minus k bits parity. So this redundant bits that we add to that is called parity bits. So the final thing is n bits, is the code length encoded signal. And this is the channel encoder. So it adds redundancy. We have only k bits, but we need to add n minus k bits to that in order to make sure that our reconstruction error that I talked is as small as possible. So the code efficiency is equal to k divided by n, which is called eta. And eta is always between 0 and 1. The code weight is the total number of non-zero bits in a code. For example, 11011001. If you count the number of ones is 5. So the code weight is 5. And your parity could be even or odd. So the total number of ones is odd, or even if the total number of ones is even. For example, your message is this, so the total is 4, and if you add noise to that, suddenly it becomes this. So let's see what we have missed. Oh, this one. We have missed this one. But we don't have any problem. So here is 3. So we had 4, now we get 3. So we need a retransmission request to be sent. So you get the idea, because it is an even parity. You cannot expect to have odd parity, odd sum of ones to be odd if you don't miss any if noise doesn't affect on that. So now you may guess that, oh,